Welcome to Cheap Controls. We make videos on things that we struggled with, hoping to help you so you don't. Consider subscribing and hitting that bell. In this video, I'm going to go over how to display a waveform on the Nextion, which I've done in the past, but in this case, I'm going to use an accelerometer to show real-time data. The hope is to get to a point where if I shake the accelerometer, you see the data on the Nextion display like that. Before this, we're going to start in the Nextion itself. For the display, and when we get to display the data on it, all we're going to have is this waveform object on the page. And I have it expanded to the extent of the page. But for those that aren't familiar with the waveform itself has an attribute called CH. And that's just the number of channels that it can display. In this case, I've chosen 3. When you first put the waveform on the display, it defaults to 1. And so when you try to send data to it, if you leave that set at 1, you won't get the other channels, what you're trying to say. And I get that wrong a lot when I'm doing it. So I always have to go, why isn't it showing the data? And then I have to go back and add the other 2 channels. This PCO 0, 1, and 2, it's going to show the color for each channel, because you want to be able to tell the difference in the lines as they go across the screen. I've added a timer to the project, and I'll remove that when we go on to the Arduino, but just to show you what the command structure looks like. So I have the timer set to go every 50 milliseconds. The way the command itself works is you type the word add, and then you have to add the object ID, and the ID of that graph or the waveform is 1. And then the next thing you add is the channel, 0, 1, or 2. It's kind of strange. In the attribute, you select 1, 2, 3, 4, but in here it's 0, 1, 2, or 3. And in this case, we'll make it 1. And then the value you want to write. Now, we're just going to write the same value to channels 0, 1, and 2 over and over and over again. But for this example, I'll make this be 70. So we're going to write 50 and 70 almost simultaneously to channel 1. So we'll see what this looks like. Now you can see there's 2 lines, the bottom line and the top line, and then this bar going across. And the bar is going across twice as fast. And that's because we're writing to that middle value, or that channel 1, twice. So it's going to add 2 spots for each one, and it's drawing a line between it really fast. It's not really solid, but for this example, it's going to look solid. So if I take this and I delete this, and now I'm only drawing 1 point on each wave every time the timer times, the line should stay even. And you can see now they're staying even, but the other time it was going between 50 and 70, and it was just drawing up and down really fast, so it looked more like a bar. So when we're over in the Arduino, we're going to have to send this command, add 1, 2, or whatever channel, and then the value. And notice that there's no quotes, so it'll just be a single string that we send up. Now I'm going to move over to the Arduino. I'm going to use the standard configuration for this example, and you'll see that I have 4 tabs. And I'm going to have this main one up here, and then CC stuff, which we're not going to use. And we're not going to use any input from the display itself. We're just going to use this delay. And the way I have the delay set up here is every 1,000 or every second, 1,000 milliseconds, we're going to go to this delay and run the function that I have in that delay tab. In my case, I'm using an Arduino or a Nano, so I need to leave the software serial in here. If you're using a Mega, you can comment these 2 lines out. So we're going to use this wire.h library, and that's what configures that I2C. And then note that the SDA is on A4 and the ACL is on A5. I can never remember what those are, so I put the note in there. Now in the setup, I'm going to initialize both the serial ports so I can see it on the serial monitor and I can see it on the Nextion display. I have this pin mode 13 set to output, and that's for the delay, so you can see the onboard LED turn on and off. I'm going to comment that line out when we get to that port, and I'll explain why. And then I'm going to print a string called starting I2C because the next command is wire.begin, and that's how you start the bus and make it configurable or accessible to the Arduino. Then I'm going to delay 200 milliseconds, and then I'm going to print out configuring the power management register. Now this part you might need and you might not need for your device. I fought with this accelerometer for a little while because I couldn't get it to read any data. And then I read a blog that's explained that sometimes you have to configure this register. So when you do this, you do a begin transmission, and each device on the I2C bus is going to have its own address. And for this one, for the accelerometer I'm using, it's 68 in hex. And then you select the register on that device. In this case, it's 6B, and that's the power register or the power management register. And then we're going to write a bunch of zeros to it, and then we're going to end the transmission. And this is the register. So every register within the I2C device will have an ID in front of it or a location. And in this case, it's 6B or 107 in decimal. You can identify it either way. I like using the hex values because the hex value is divided into two nibbles or two 4-bit representations of the number. And every register on the I2C device is 8 bits. So you have a nibble on one side and then a higher nibble on the other, and they correspond to each side of the hex. I'll describe that in a little more detail when we get to reading the data. But in this case, we're just going to set everything to 0. And here's why we set that, because we don't want to reset it, and setting that bit or bit number 7 to 1 will reset the device. We don't want to put it to sleep, so we set it to 0. And this is the thing, I was wondering if my device came with this sleep bit set 1, because it just kept reading 0 and I couldn't get anything to go. But after I set it once, I commented out those lines and it worked just fine. So I don't know if your device, you may be able to not include these lines in your code. And then I didn't want it to do this cycle either. In order to make it cycle, you set it to 1. And I didn't want to disable the temperature sensor, even though we're not reading the temperature sensor in this video. I leave it to 0, 2. And then we have this clock select down here. And the clock select has 8 different settings for it. And to be honest with you, I'm not sure what all of these mean, but I just wanted it to use the internal 8 megahertz oscillator. So I set all those bits to 0. And that's how we get to this wire write of 0. So we take that register location of 6B and we fill it with zeros. And then we have the delay of half a second. And then we're going to configure the gyroscope register. And we do the same thing. We begin transmission to the device ID, which is 68. And then we select the register. The gyroscope is 1B and the accelerometer is 1C. And then we're going to write the values of 1, 0 to it. So this is register 1B or 27 in decimal. And these first 3 bits are self-test bits. And I have yet to set those to 1 and see what happens. So I always leave those 0. And then we have these 2 bits, 3 and 4. And this is going to set the scale that we're going to use. It could be 0, 0, 1, 0, 1 over here, 0, or 1, 1. And of those 4 settings, we have a degree per second range of plus or minus 250, plus or minus 500, plus or minus 1,000, or plus or minus 2,000. And that's the number of degrees per second that we register on the device. And I set it to 1, 0, which is 2 in binary. So I'm doing the plus or minus 1,000 degrees per second. And after we configure the gyroscope, we'll configure the accelerometer. And once again, we do the device ID, which is 68. And then we're going to write to register 1C, and we're going to write the values 0, 8. And the accelerometer configuration is very similar. We have these self-test bits, and then we have these 2 bits that surround the different nibbles, and that's where we select the setting. And I have it set with a 1 here, because 1, 0, 0, 0 is 8, and then I have all zeros over here. So it's the value number 1, or the second setting. So I've chosen 1, which is plus or minus 4G. And then once we have that set up, we're going to wait another half a second, and then we're going to jump down into the main loop. Now in the main loop, I'm not going to make any changes at all, because all we're going to do is every time it runs this asynchronous delay, which is every second, we're going to jump over to the function delay function. And that's over here on the delay tab. And right now, all the delay function does is flash that LED, that onboard LED. And we're going to speed that cycle time up. So I'm going to comment out that LED so it doesn't flash too quickly, because I'm going to set it at 10 milliseconds eventually. And initially what we have to do is we have to set the address that we're going to be looking at to the proper location or the proper register where the data will be stored for the accelerometer or the gyroscope. Accelerometer data is stored in the 6 bits starting at 3B. So 3B, 3C, 3D, 3E, 3F, and 40 or 40. The data on an I2C device is as 8-bit chunks, but the data for the accelerometer is a 16-bit readout. So it's broke up into 2 sections, the high bit or the high byte and the low byte for the x-axis, the y-axis, and the z-axis. They all have a high and low byte. Down here, the gyroscope does the same thing. It has the x, y, and z axes, and we have the high and low bytes. But it starts at 43 and goes up to 48. And we're going to start by looking at the accelerometer. We have it set to 3B. And once we set that, then we have to end the transmission again. But we're going to set it to false because we're not truly going to end the transmission. And since that the registers that we're going to be reading are 2 bytes each, and we have 3, we're going to read 6 bytes every time we go to access it. So this is where we do the request from. We're going to request from device 68. You'll get very familiar with the device name if you do it this way without a library. But from 68, we're going to request 6 bytes, and after we have those 6 bytes, we're going to end the transmission. That's what the true means. All we have to do is have the command wire.read. We don't have to tell it the register, and we don't have to tell it to increment the register. Once we've made the request from for 6 bytes, every time we do a wire read, it's going to grab the current register, and then it's going to increment it by 1. In this case, we're going to do 2 wire reads on each one of these lines, and we're going to store it in a 16-bit short called XRAW, YRAW, and ZRAW. I've called it raw because this is going to be the raw data. So the first wire read is going to be 8 bits. And we're going to collect that, and then we're going to shift it over to the left 8 spots. So it'll be the 8 bits, and after we shift it, it'll be 16 bits long, but what we read will be in the leftmost 8 bits, and the rightmost will be zeros. And then we're going to do another read, and we're going to OR it with that original read. So we'll take whatever's a 1 will stay a 1, and whatever's a 0 will stay a 0, but it will be combined across 16 bits. And then we're going to store it in this XRAW. We're going to do the same thing with the Y and the Z. So this way we'll have all the raw data for all the axes. So now the values are coming in as this short, the 16-bit short. But we have to convert it to a number, a value from plus or minus 4. And we do that by dividing the raw data by 8,192 and then converting it to a float so it can be a decimal point. And the way we come up with that is in this chart. So if it's plus or minus 2, G, 4, 8, or 16, that means that each one is equal to this value over here. So if we take that value that we've got, that binary value, that X raw, and divide it by 16,384, we would get the value between -2 and 2. But in our case, we're using the 4. So we have to divide it by 8,192. So we're going to cast it as a float, and then we're going to store it in a float. And we're going to divide that raw data by 8,192. So now I'm going to use the serial port to print the value. So I'm going to pull that up next. So I'll upload this to the Arduino and then show you that. And you can see here it went through all the steps. It configured the power management register, then the gyro register, and then the accelerometer register. Then after that, we're getting data out. Now I've set the auto scroll off. I'll turn it back on. Now if I adjust the accelerometer, you can see that we get some movement on it. But on the serial monitor, it's not very clear. It's easier to do this, or better to do this in the serial plotter. The other thing too is we want to speed up the data. We're going to go back to this main tab, and we're going to change this to 10. So now what we have is a delay length of 10 milliseconds. So this will make the data coming from the accelerometer a lot faster. Now instead of the serial monitor, we're going to select the serial plotter. Now you can see that the data is going across. I'll reach over, and you can see me grabbing the accelerometer, and as I wiggle it, you can see that it changes on the serial plotter. So now we want to get the same data going onto the screen. So if I minimize this, we want to see it showing up over here. And this is pretty simple because we already have the data and we know the command that we need. It's just that add command. One thing I forgot is up here, when we're doing it to the serial plotter, you need to have your title, which we have x-axis : all one, no spaces in it. It has to just be the title, and then you need a space, and then the data itself, in our case that x float. And then you end it with a /t. And that lets you know, that lets the Arduino or the serial plotter know that the title is x-axis and then the data is the data. And then that /t lets the Arduino know that you're going to have more. Or if you have a double /t like at the end, after the z-axis, that /t, and then we print another /t, it lets the serial plotter know you're at the end of the data, and the next time around, start a new row. And that's how we're able to do the 3 different lines. Now when it comes to the Nextion, we send that add for each channel, 1, and then for the ID for the device, or the waveform is 1, and then the channels are 0, 1, and 2. But instead of sending a value from -4 to 4, the first thing we have to do is shift all that to a positive value. So instead of -4 to 4, we're going to add 4, so it's going to be 0 to 8. And since we have 8 integers, because all that the Nextion knows is integers, so we have 8, we're going to keep it in xfloat form, at least at the beginning, and we're going to multiply it times 30. And how we come up with 30 is, since we have 8, the value is 0 to 8, but we have to transfer that or map that to a value of 0 to 255. 255 and divide it by 8, and we get like 31 around there, but I just left it 30 for reference. It's close enough for the video. So we'll take that x float, we're going to add 4 to shift it up, and then we're going to multiply it times 30. And then that way it will represent the whole screen. If we had a value at 4, it would be very close up to 255. A value at 4, or at 0, which would be 4, is 4 times 30, which would be about 120 in the middle, and then 0 would be 0. I'm going to upload this and then show it to you on the screen. You can see it did some adjusting here because I was messing around with it before, and now this is the actual data coming through. So now when I grab this, we should get a nice wave. It's not super clear on here. I need to get a better camera, I guess. But if I do it slow, you can kind of see it. Looks pretty good. If you'll notice that the accelerometer, it holds its position. So as I turn it or adjust it, it changes and then it flat lines out. Whereas the gyroscope, everything's zeros, and then based upon the movement, it'll change. We're going to switch that and go to that next. So on this delay loop, where we do the wire right and we select that register for the accelerometer, that 03B, all we have to do is change that and select 43. And now we're reading the data from the gyroscope. Now, in order to get this a little more accurate, we would have to go through and change these values in here, 8192, because we would divide by a different resolution or a different scale for the gyroscope. But in this case, we're just going to leave it alone because we're going to get a value between some binary value between 0 and whatever 16 bits are. So it should display okay and give you the idea of what it is we're doing. You can see the screen is still reading out, but when this code loads, all of the lines should come together around the 0 point. And there you can see that they've come together now. So all of the axes are at 0. And then when I do the movement on it, they change. So this time I'm turning it this way. And if I turn it this way, you'll get a different. And if I just shake it around. But when I'm done and I stop, they should go back to 0. Now in this case, it's not a great readout because they're all on 0. So what could you do if you wanted to separate out the lines? So what I'm going to do is I'm going to come back here and I'm going to change this first one to +2. I'm going to leave that one at 4 and change this one to 6. And then I'm going to upload this. And now when it's uploaded, you'll see the lines on the screen will separate. Because you can see that one of the axes is going to be at 2, one will be at 4, and one will be at 6. Now they will go off the screen, but at least it's separated so you can see the different. So you can see that bottom one is the rotation to turn this way. And if I go this way with it, that's the top one. And if I go a different way with it, it's the middle one. So you can see all three axes independently. But you can also see that it's pretty easy to add different waveforms and send multiple channels to the Nextion from the Arduino. The code in it is only one line of code, and it's just this add command. So you do the add, the device number, the channel number, and then the value. But you do have to make sure that in the Nextion display itself that waveform can accept the data. And you do that by setting up the number of channels on the Nextion before you start transmitting data from the Arduino. And as I said at the beginning, that's one of the things I get wrong a lot, and I have to go back through and redo, because I'll be sending 3 channels and go, oops, I'm only seeing 1, I know what it is now. So I just go back to the Nextion, reload it, download the code, and I'm good to go. Now this video is going to be tied to the one I did a few weeks ago with the Lux blocks and the spinning of the fan, because I want to hook this accelerometer up to measure the vibration on the fan. As I've also been told that you can tell the RPMs using the vibration sensor. So I want to see if that's true. I've never done it before, but I want to check it out and see. So I might also hook up a Hall effect device that will give me the actual RPM and compare it against what we see with the accelerometer. Well, that's about it for this video. If you like what you saw, consider giving me a thumbs up, and also consider subscribing to the channel. Thanks for watching.